Hello, AP biologists. Mrs. Grider here to talk about Hardy-Weinberg Equilibrium. All right, so this presentation will have a background on Hardy-Weinberg Equilibrium and then some practice problems. And there are points of the presentation where you should be prepared to work along with me. So, in general, Hardy-Weinberg Equilibrium is the term that biologists use to describe when a gene pool remains constant over time. What's a gene pool, you ask? Well, a gene pool is all of the alleles or versions of a particular gene in a population. So here in my example, if each one of these circles is a person, then a capital A is the dominant allele and a lowercase a is the recessive allele. And the gene pool refers to all of these alleles that are in this population. So in the population that I have right here, I have 10 alleles. 5 people, 2 alleles each, because that's how our genes work. We get one copy from our mom and one copy from our dad. And my population in this picture is at Hardy-Weinberg equilibrium because you can see that my gene pool remains constant from the beginning to the end. Now I want to be clear. This doesn't mean that the individuals in the population necessarily have the same traits or even have the same genotypes. What it does mean is that I have the same number of alleles that are dominant and recessive over time. Let me show you what I mean. So over here you can see that 1, 2, 3 of my people have the dominant trait. They've got that capital A allele. And over here, 1, 2, 3, 4 of the people in my population have the dominant trait. So the number of people with the traits didn't stay the same. However, if I actually go back and count the alleles, I can see that I have 1, 2, 3, 4, 5 dominant alleles on the original population, and 1, 2, 3, 4, 5 alleles in the existing population. And so what that means is I had 50% dominant over here and 50% dominant on this side as well. My gene pool overall has remained constant. How did that happen? Okay, let's look at it. So over here I can see that I have some homozygous dominant individuals and some homozygous recessive individuals. And if these people, for example, this person and this person had a baby, it might end up looking like this, a heterozygous individual that got a dominant allele from one parent and a recessive allele from the other. But we can still say that this population is in Hardy-Weinberg equilibrium because the overall percentage of each allele in the gene pool remained constant over time. This essentially means that my population is not evolving because all of these alleles have remained. None of my alleles have gone away. So that means that these people could have babies and we could still have the same proportion of dominant and recessive alleles. An easy way to remember that is in Hardy-Weinberg equilibrium, what we're saying is that the population isn't evolving over time. The alleles in the population, the genes in the population aren't changing. Instead, they're staying constant even as time passes and new generations are born. So there are a bunch of requirements for Hardy-Weinberg equilibrium, and I've listed them here, and each of them has to do with one of the mechanisms of evolution that is possible to happen in a population. So, for example, I'm going to write over here the mechanisms of evolution that we talk about with each of these things. So, for example, the population must be very large, and this is to protect against genetic drift. Genetic drift are those random events or random chance, which means that some individuals are more successful in a population than others. Doesn't mean that they're any more fit for the population, they just happened to survive a natural disaster or have more babies in a certain generation. And genetic drift happens much more quickly in a small population because random chance can overtake a small population very quickly. So if the population is large, it's less likely to evolve due to genetic drift. The population must be isolated from other populations. No immigration or emigration, we also call that gene flow. And this simply means that the population is not going to evolve because individuals with certain genes leave or new genes come into the population. All right, no mutations. That really doesn't have anything that goes along with it. It's just that we're not creating new genes because if we have a new gene, then it might be more fit for the environment and the population might evolve. random mating. This means that there is no sexual selection. No sexual selection. And that means that certain individuals do not have traits that make them more attractive for a mate. Mating is totally random. Everyone is equally likely to have babies. And lastly, no natural selection. Every individual has an equal chance to survive. There are no selective pressures. No one is more fit. And if all of these things are happening, in the population, then that means that there is no evolution going on. No evolution. The genes are constant over time. The population is not changing over time. Everything is constant. No evolution. This doesn't happen very often, if ever, in real life, but it's a way that scientists are able to say, if a population is not evolving, it would have all of these characteristics. Therefore, we can make comparisons to populations that are evolving and state reasons why they're evolving. And then when we look at the numbers in Hardy-Weinberg equilibrium, we can actually quantify that those populations are evolving by virtue of looking at how the frequencies change. So let's look at that in the next section. So I've included the two Hardy-Weinberg equations here at the top. And the Hardy-Weinberg equations are always provided for you. They're on the AP formula guide, so you don't have to worry about those. But you do have to know what they mean. So I've broken it down into this chart that we've used in class and that you need to know by heart because no one's giving this to you on the test. So I've broken it down into phenotypic frequencies, genotypic frequencies, and allelic frequencies. All right, so let's fill this out. So for phenotypic frequencies, this is referring to the traits. Genotypic frequencies are referring to genotypes, which are the two alleles that every individual has. And then the allelic frequencies are referring to the overall percentage of alleles in the population. So this is each allele. All right, so if I look at this, change my color here, I'm going to start with allelic frequencies and work my way to the left from there. So the allelic frequencies are laid out, and this is the key here for P and Q. So P is the dominant allele, and Q is the recessive allele. And this is the overall percentage or frequency of P and Q in the population. Not in any individuals, but in the population overall, how many dominant alleles are there and how many recessive alleles are there? If I go back to my initial example that I saw on the previous page, when I counted the dominant alleles, there were 1, 2, 3, 4, 5 out of 10. So that would have been 5 out of 10, 50% would be my value for P, because half of those alleles are dominant. Now, Q is the recessive allele. And overall, P and Q always add up to 1 because those are the only two options. P plus Q has to equal 100%. All right, genotypic frequencies. I'm going to zoom in a little bit so I can write a little bit easier here. And in my genotypes, I've got 3 different potential genotypes. I can have homozygous dominant, I can have heterozygous, also known as the carrier, and I can have homozygous recessive. And these frequencies are found here in, let me change my color again, in this equation. So I have homozygous dominant is represented by P squared. Heterozygotes are represented by 2PQ, and homozygous recessive is Q squared. Now, this is really important to keep separate from the allelic frequencies. Genotypic frequencies refer to the number of individuals in the population that have this set of 2 alleles. Allelic frequencies are the percentage of dominant and recessive alleles in the problem overall. Very rarely will a problem be kind enough to give you the allelic frequencies outright. They're much more likely to give you the genotypic frequencies and make you figure it out. So genotypes are something that we see in people. Allelic frequencies are not. The other thing that we can see in people are the phenotypic frequencies, which are my traits, which are also in people. And with our traits that we see in people, we once again have dominant traits and recessive traits. All right, now using what we know about genetics, recessive traits, the only way you can get a recessive trait is if you are homozygous recessive for the genes, if you have 2 recessive alleles. So in that case, you would be Q squared. That is the only way you can get the recessive trait. However, people who are homozygous dominant for a trait and people who are heterozygous for a trait are have the dominant trait inside them. So if I go back to my previous example, this means that people who have 2 dominant alleles who are homozygous dominant have the dominant trait, as well as people who are heterozygous, because they have one of those dominant alleles that is going to cause them to have the dominant trait. So that means that the people who have the dominant trait are actually 2pq, my heterozygotes, plus my homozygous dominant, p squared. All right. Make sure that you know this by heart when you walk into the exam because, like I said, they'll give you the equations, but that's it. Right now, I'm going to walk us through 2 problems, and this is a great time to pause and try and work out the problems yourself. So, I'm going to put this right here. It's the simple Hardy-Weinberg Equilibrium problem. Pause this on your computer. Try and solve the simple problem by yourself. I hope that you've done that question on your own, and now I'm going to walk through how to do the simple problem for Hardy-Weinberg. So whenever I do this, I try and tackle problems in the same way. I look at what information they give me, and I try to figure out where does it fit in terms of alleles, genotypes, and phenotypes. Then I figure out what information they're looking for in the problem, and I do the same thing. I figure out, is it an allele, a genotype, or a phenotype? And then I use my friend Q to help me solve the problem, because almost every time that works. So let's walk through it step by step. So step 1, I'm going to look at the information that they give me. So it says, within a population of butterflies, the color brown is dominant over the color white, and 40% of all butterflies are white. This is the information that they've given me. Calculate the percentage of butterflies in the population that are homozygous dominant. Okay, so they gave me information about a trait. It's a color. So that is a phenotypic frequency that they gave me. So I think about how that fits in. It's 40% are white, which they said is not dominant over the color brown. The color brown is dominant over white. So that must mean that white is the recessive trait. Okay, so they told me 0.40 or 40% of my butterflies have the recessive trait, which means that they are Q squared. Now, I am trying to find the percentage of butterflies that are homozygous dominant. Well, when I look at that, that isn't a trait or an allele, that's a genotype. I'm looking to find the homozygous dominant genotype. Okay, so homozygous dominant. If I look back to my chart or remember it, that is P squared. So that is what I'm trying to find. Okay, they gave me Q squared, I have to find P squared. And in order to do that, the best way to do it is with my friend Q. Okay, so Q, how can I find that? Well, they gave me that 0.40, let's do this in blue, 0.40 equals Q squared. Okay, well, if I take the square root of each side, I can find Q. So let's do that. 0.40 square root. 0.40 square root. I put that into my calculator. I'm using my phone right now because it's the dumbest calculator I have, and we know that we have to use our dumbest calculators in order to solve these problems for the AP Bio test. And Q is then 0.63 when I do that on my calculator. All right, Now, if I go back to my Hardy-Weinberg equations, I know that P plus Q equals 1. That's circled in blue at the top. So P plus 0.63 equals 1. That's pretty easy. I subtract 0.63 from each side, and P equals, using my dumb calculator again, 0.37. All right, I'm almost there. I have the percentage of dominant alleles in the population, but that doesn't tell me the percentage of homozygous dominant individuals in the population. That just gives me the number of alleles. So I still need to find P squared. So I'm going to square both sides on this, 0.37 squared, and that is 0.14, or 14%. All right, so that is how I solve my simple Hardy-Weinberg equilibrium problem. All right, here's a more complex Hardy-Weinberg equilibrium problem that might be a little bit more like what you see on a test. Pause your computer, try to solve it on your own. Okay, now that you've done that, I'm going to walk you through it step by step. I'm going to use the same method as I did before. I'm going to do what information did they give me, what are they looking for, and I'm going to use Q in order to find out. Okay, so they told me that cystic fibrosis is a recessive condition that affects 1 in 2,500 babies in the United States. Then it's asking me to calculate the percentage of heterozygous individuals in the population. Okay, this question is a little bit more complicated, mostly because of the way it's worded, but in actuality, it's pretty similar to the one that we solved before. So let's look at what they gave me. Recessive condition, okay, that's a trait that somebody has. Anytime they give you a disease, that's a trait, a condition. And then they gave me that it was 1 in 2,500 babies. So instead of giving me a nice frequency to work with, I'm going to have to calculate that by myself. So 1 in 2,500 have a recessive trait. If I look back to my chart, or if I'm good and I have it memorized, I know that that is Q squared. And I'm going to actually calculate that out now on my calculator. So 1 in 2,500, that is 0.0004. All right, now they're asking me to find the percentage of heterozygotes. So they're asking me to find the carriers. That is 2PQ is going to be my carriers. All right, so how am I going to do this? I'm going to use Q. So I already know 0.0004 is Q squared. So if I take the square root of that, all right, let me do that. Square root of 0.0004, I get that Q is 0.02. All right, now that I've found Q, I need to find 2PQ in the end. So in order to do that, I'm going to have to use my P plus Q equals 1, P plus 0.02 equals 1, which means that P is going to be 0.98. Be really careful with your decimal points. I actually did this before and made a mistake with my decimal points and had to go back and refilm it for you. So now that I have P and Q, 2 times P times Q, 2 times 0.02 times 0.98 on my calculator gives me 0.0392. So there's one last way that they can make this question tricky. They might ask you for a specific number of individuals in a population that have a certain trait. So for example, they might say, if there are 2 million people, how many people are carriers? See if you can solve that based on what you know. All right, so if they ask you for a specific number of people, you have to remember that you've just found a percentage of people in the population that have that trait. So we know that 0.0392 or 3.92% of people in the population are carriers. So in order to apply that to this last step, which they might throw at you, I would simply multiply 2 million by 0.0392. So I would say 2 million times 0.0392. I know I'm running off the screen there, but if I solve that, 2 million times 0.0392 I get 78,400 people in the population. So if it asks you for a specific number of organisms, all you need to do is find the frequency and multiply it by the size of your population. All right, email, text me, tweet me if you have any questions. Good luck.